All right, motion. So you know if you drop something and let it fall, okay, it's going to fall, right? And you may know that it's going to go fall faster and faster and faster. So we say if something goes faster and faster and faster, that's a form of acceleration. It's changing its speed, okay? And this is actually trying to show you Galileo, I believe, dropping something off the Leaning Tower of Pisa, okay? And notice that he dropped two objects. The one on the right looks a little bit larger than the one on the left, okay? But one of the things that he proved that actually those two objects, the one you might think the one that's heavier is going to fall faster, they fall at the same rate, okay? And they go faster and faster, 9.8 meters for every 1 second they fall, okay? Regardless of mass. Now, I'm not going to cover it much. It didn't make it to my slides this semester, but your textbook talks about something called terminal velocity. And there is something to be said for aerodynamics of the object that you're dropping. Okay, if you've ever taken a physics class where your object, the goal was to drop an egg and make it land safely. Okay, so there are ways to slow down your rate of fall. Okay, but that's and there's something called terminal velocity, which means the fastest velocity you basically max out, depending upon, again, kind of the aerodynamics. But we're pretending, and we're not. It's not too far of a stretch, that actually all objects will go faster and faster and faster at the same rate, regardless of their mass and kind of their configuration. So how much faster they go each second they fall is 9.8 meters per second. So meters per second is a speed or velocity. And so for each second they jack it up, they add 9.8 meters per second onto their speed. All right. It's Monday. Was there another line there, or was that all? That looks like that was it. Good. So one of the things, well, how are you going to prove this, right? Because I said the whole aerodynamics get in the way of climbing to a roof and dropping things, okay? Well, one way is to basically create a vacuum, an environment where there are no, because the thing that creates drag and creates difference between, aerodynamics is air. So if we suck the air out, like of this cylinder, then you can finally take a feather and a penny, and I don't have the apparatus to show you how we can do this, or to do this for you, a live demonstration. But if you suck all the air out, these two things are gonna go accelerate at the same rate. The feather and the penny will drop and hit the thing at the same time because you sucked all the air out. Alternatively, actually, I guess I did include a term called terminal velocity. Alternatively, what's that?
That's the fastest, right?
Yep. Terminal velocity was what I was kind of describing a minute ago, that objects that fall in the air, objects that fall and they're interacting with air molecules, they will have a terminal velocity. Yeah. So an alternative to taking a cylinder and sucking all the air out is to go into outer space, quite frankly, where there aren't little air molecules to give you to put a drag on things that are falling. Okay, so I'm going to hopefully play this little video for you. This is a classic. Nope. Nope. Maybe I'll play it for you next time. What this black thing, this little video would have been is when they went to the moon, one of the Apollo missions actually took a hammer and a feather, and he did his little speech, and he said this is one of the things that Galileo proved and Newton also supported. You drop them at the same time, and the hammer and the feather will hit the moon at the same time. Okay, There's no air to give them to make it otherwise. So one of the things I need to say sometime right about now is that actually the reason they're falling is because of gravity. The reason they're falling is because of gravity. Remember, Newton came up with that equation, the force of gravity is equal to gravitational constant times the mass of each of the things that are connected to each other or gravitationally attracted to each other, divided by r squared, the distance between those two masses. So that is what's making things fall, the force of gravity. All right. So actually, this is a repeat slide. I guess you don't have the slide, do you? You have something next. But if you want to, in the margins, kind of put this, but you already have this equation back a few slides ago. This is why feathers fall, pennies fall, hammers fall to the moon, to the earth, okay? This mutual attraction between the two objects. So one of the things I want to emphasize is we talked about how mass, the amount of matter an object contains, and weight are two different things. So I want to kind of reinforce that. Whenever you get on the scale or we talk about the weight of something, that actually is the force of gravity working on that object. And I want to emphasize that, or mention, down here, right here, where you see that little person standing on the earth, okay, W stands for his or her weight, okay, and actually the weight, and we're going to run into this a little bit in our energy our energy chapter in chapter 3. The weight of that person can be calculated by taking the mass of that person times G, okay, where that, since they're on Earth, G is that 9.8, that's acceleration due to gravity. G is acceleration due to gravity. Okay? Where the G, the acceleration due to gravity on Earth is in that 9.8 meters per second per second. That's acceleration. And remember, we can combine those 2 seconds, and so actually that's 9.8 meters per second raised to the second power. 9.8 meters per second squared. Okay. So I haven't done it, but actually we should be able to calculate weight both using this kind of quick and dirty, the mass of the object on the Earth times the gravitational constant for Earth, and it would also be equal to going about it this way, using Newton's relationship, gravitational law. Okay, so now you have this slide though. So how does that mean when things go accelerate 9.8 meters per each second? So what you're going to see here is kind of a series of balls as they fall for 1 second, in 1 second intervals. So this is how this works. In 1 second, it will be going 9.8 meters per second faster than 0. So 0 plus 9.8 is 9.8. In the second, we're going to add 9.8 meters per second onto 9.8 meters per second. So that was, what, 19.6? 19.6 for that second. For the third second, we're going to add another 9.8 onto that. Okay, so that's how that goes. And the fourth second, it's going even faster. In each case, it's increasing 9.8 meters per second. I think that's cool. So we have another equation. Actually, this isn't another equation. This is an equation that you guys used for your homework that I think you're handing in. If you want to calculate acceleration, what you got to do is say what was the change in velocity, the final velocity minus the initial velocity, and divide the time over which that change occurred. Okay, so that's something we've already run into. So calculate the acceleration from 0 to 4 seconds. So let's do that. I brought my calculator. Get your calculators handy. So average acceleration, the final velocity looks like it's at 39.2 meters per second. The initial velocity was 0 meters per second. The time over which that change in velocity occurred was 4 seconds. And not so surprising. Did you do it? Did you do it?
Mm-hmm.
What is it?
9.8.
It is 9.8. Thank you. 9.8, and that's meters per second, okay, per second, or 9.8 meters per second squared. So it's just kind of what we've been doing. But we got the constant associated with gravity influencing objects as they fall towards the Earth. So here's another look at this equation just to kind of show you how this is the one that we just used, okay? I'm going to flatten it out and I'm going to show you how we get that, the new equation. So one of the things I like to do is I like to kind of think of this as over 1 and kind of crisscross, cross-multiply to flatten it out. Okay, so if I flatten it out, now I've got AT is equal to VF minus VI. And then trying to clean it up to get it something like that. It's not too bad. If I want to get the final velocity by itself, I could what? Add the initial velocity to both sides. Does that make sense? Then, of course, these go away. Okay, and actually now you have this up here. The reason kind of going through that to get the final velocity by itself over there on the left, that's just kind of nice because now if you want to solve for the final velocity, that's kind of what we do. We put it on its left. Then we can solve if we know the initial velocity, the acceleration, and if it's on Earth, something accelerating falling on Earth, it would be 9.8 meters per second, and then the time. There's one other kind of form for that then. If it starts at rest, okay, if it starts at rest, that means V sub I, the initial velocity, is 0, so that term goes away. So things are even easier if it's at rest. So this one is a special case here. This is if this is equal to 0. So this is helpful if, for instance, you are dropping an object from the Leaning Tower of Pisa and you want to know how fast it's going to be going at any given time. You can automatically kick that out. That's what that will do for you. So I think we have an example coming up. So let's say you drop something, okay, and you're going to let gravity kick in. You're on Earth, so you know the acceleration due to gravity is 9.8 meters per second. How fast is it falling after time is equal to 5.2 seconds? So we're just going to use that equation right above. We can use this because the initial velocity is 0, because you're dropping it from the roof. Okay. So the V sub F, the final velocity. Now when you work these, I need you to include units. So since this is on Earth, we're going to use that 9.8 meters per second times the time. The time is 5.2 seconds. And multiply those out. Looks like we're going to give ourselves two digits. And I got 50.96. And if you write that, you're gonna be in good shape. But for 2 digits, do you see I'm going to have to round it to the ones? So actually, that's going to be 51. But to get full credit, what are units going to be? I thought that, but now I'm thinking again, what are units of velocity? It's not meters per second squared, what are units of velocity? Let me think. Here's one way, and if you're into the whole factor label method, actually, oh, you know what? Drat. I should have put a squared there. If you're into the factor label method, actually these seconds right here in the time cancel with one of these seconds here. So just meters per second. Yep. Sorry. Very good. Make sure you put at least some units down. And then go back and look at your work and see if it makes sense. Okay. So that's how fast you'd be going in 5.2 seconds. Okay, here's a little bit different, and now something's not falling, but now we're saying that something is powered, and this car is being powered, and it's accelerating. So let's go ahead and draw a picture for this one. So here is my car. Oh boy, not very good car. Oh, and it is accelerating. Okay, at 5.41 meters per second squared. So acceleration, I'll go ahead and put a little bar over it. If you don't put the little line over acceleration, you'll be okay in this class. But average acceleration is 5.41 meters per second squared. Okay, how long will it take to be traveling 22.4 meters per second? So does this make sense? This 22.4 meters per second, that is the v sub f, the final velocity. And I'll go ahead and diagram down here. How long will it take? So this is question mark t. How long will it take? So we can actually still use this final velocity is equal to acceleration times time, but what I like to do is kind of reorganize it a little bit so my time is over there on the left, or by itself anyway. I'm going to get it by itself first. I'm just going to, if you're okay with this, take this relationship over here, and I'm going to, if I want to get time by itself, I need to divide acceleration, divide by acceleration. Divide both sides by acceleration. If I do that, then my accelerations cancel. And so I can rewrite this. I'll rewrite it over there. And it would look like this. I'll go ahead and put t. I'll put it over there on the right, or excuse me, on the left, because I like it on the left. T is equal to v sub f over a. By that, t is equal to v sub f. So then we're just ready to plug in. So in this problem, t is equal to the final velocity we said was that 22.4 meters per second. Divided by acceleration. And acceleration is 5.41 meters per second squared. Okay, I'm going to divide that out and see what my calculator displays. I got 4.1481484, yeah. So it looks like I'm going to round to 3. I didn't divide it out right. I'm going to give it 3 decimals. I got a 5.41. There. Now I got 4.14048. Okay, good. I'm going to go with 3, and so I'm going to take the first 3, so I'm going to vote 4.14. Now, this is a time. What do you think units of time are then? They're simply seconds. Perfect. I'm going to show you how that works. So these meters both cancel. One of these 2 seconds cancels. Okay, so honestly what we have unit-wise is we have 1 over seconds in the denominator. So if you have a ratio in the denominator, you can flip it up and bring it up into the, bring it out from the denominator by flipping it. So actually this is units of seconds. So we're cool. But if you just want to know, time's got to be seconds. That's it. Okay? I like it. Okay, so this is due, and I think I've got this. We can take a look at it together right quick. Just this one problem. And I double checked. There's no conversions. So page 50, problem number 16. Let's kind of look at that right quick. So it looks like this one, number 16. What speed does the ball in exercise 15 have, falling 3.5 seconds? So I kind of went ahead. I hate it when they say problem 16 refers to problem 15, right? Like, oh. So I went ahead and showed you problem 15 there. Problem 15 refers to this figure, okay? So problem 15 refers to this figure. Problem 15 says a ball is dropped atop a building that is 80 meters, okay? And it says, does the ball reach the ground in 4 seconds? And then I think this is just by observation. This isn't question 16, this is question 15. But I think, oh, there it went away. Come back. But I think if you just look at the figure, you know that at 4 seconds, it didn't reach the bottom, because at 4 seconds, it's close. It's 0.8 meters away. Okay, wait. There it is, 0.6 meters away. I was looking at the wrong thing. It's 0.6 meters away. So it doesn't quite reach the bottom of the 80-meter building, or the ground. So based upon that, that's kind of a side. 16 says, what speed does the ball have when it's falling 3.5 seconds? Well, I want you to use the equation, but it never hurts with problems like this to kind of look at, okay, do you see where this is between 3 seconds and 4 seconds, 3.5 seconds? So you're like, oh, I probably should get a velocity between 29.4, not exactly between 29.4, but somewhere amidst 29.4 and 39.2. I guess it would be just exactly. Okay. So it's not too bad. You guys can do it right now, I'm sure. So.
Why couldn't you just take your original 9.8 meters per second times 3.5 seconds, because that would give you...
That is what you're doing, Grace. Yep.
I'm just kidding.
Yep. What she just said was just what the formula says.
Right.
Yep. You got it. You got it. Yep. Any questions? Good. So kind of, if you're like, well, I wonder what the test is going to look like in a few weeks, what I'm going to do is like the problems like we worked in class and or the homework problems, those are sort of what the problems are going to be like in your test. Okay? All right. So on to dun, 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 the next part. Did you have a question, Devin? Or did Heather help you? Okay. Oh, yeah, you're getting it. Nothing like doing your homework in class. Only one problem there.
that the only homework we're assigned, or we got more?
We might get to another one. Yeah. That's the only one so far. Come back. Goodness, such gyrations. Okay. All right. So switching gears a little bit, from motion to work and energy. So one definition of work, or we can say work is accomplished. The variable for work is a big W. The variable for weight is a little w. So work is a capital W. We've run into F before, force. D here, a lowercase d, is distance. So basically, if you want to know how much work you performed or accomplished, you take the force, you take an object, okay, and you have to apply a force to the object to relocate it a distance. So the work expended is the force applied times the distance the object was moved, basically. Okay? So for instance, here we show a guy who you can see how far he's relocated that crate, right? From left to right, and he relocated it a distance of d. He had to apply a force F. So the work expended is just multiplying the force that he applied. Remember what units of force are? Newtons. Okay? So the newtons he applied times the distance he applied it over. Here we have an interesting sort of thing. The guy trying to move the building. Okay? So of course you can see that here he is applying a force, but distance is 0. Okay, so if you plug into distance 0 here, I don't care if it's a force, that's whatever force it is, but can you see where the work is zilch? If he didn't move it, the work is zilch. He may have felt like he had to work out. But in this sort of context, the work was 0 because he didn't move it. So just so you know, we're going to limit our study of work just to basically the motion, the distance that it moves is in the same direction directly as to the force applied. We're not going to do any angle things in here, just because I don't want to. So we are a little bit about units in this class. Okay, so make sure as you work problems, even if you're kind of scratching your head, make sure you put a newton for forces. Forces are newtons. Distance would be meters. Okay, make sure that you use the right units. And units of work actually are the same units as energy, and they are joules. You might be familiar with the energy unit of a calorie. Okay, that's in the English system. So joule is in the metric system, so we're sticking with joules. And the cool thing about joules then is that actually, not so surprising, joules can be broken down into kind of the basic metric units. So a unit of work or energy, the joule, is a kilogram meter squared per second squared. Okay? That is kind of the nitty-gritty to what a joule is. But just remember, joule is units of work and energy. So let's do a problem. So, yep, we're dealing with the same guy who successfully relocates this crate a distance d. Okay, so let's just say he's pushing with a force of 2.5 newtons, and he's going to relocate the crate 6.12 meters. And we're supposed to calculate the work that he expended. Okay, so not too bad here. So work is equal to force times distance. The force here was that 2.5 newtons times the distance is 6.12 meters. Looks like we're going to give it, what, 2 digits? So I got 15. And what are the units going to be? Joules. Yeah, joules. You could go with kilograms meter squared per second squared also. It'd be the same thing, but we're going to go with joules. Either way, it'd be great. That's it. 15 joules. And it kind of makes sense because, you know, in fact, in this case, we said he relocated it the same distance, 6.12 meters. But here I want you to get back to using a little bit of scientific notation. And so instead of applying a force of 2.5 newtons, he applied a force of 2.3 times 10 to the negative 6 newtons. Okay. So now it looks a little bit different. And work, W, is equal to force, which in this case is that 2.3 times 10 to the negative 6th newtons, times distance, the same distance, 6.12 meters. So should work be greater or less than the other work for the first problem? Should be significantly less, exactly. So if you have your calculator handy, if you don't, you can try it when you get home. So 2.3, I'm finding my EE key. I'm going to put negative 6, that's the exponent of 10, times 6.12. And let's see, looks like we're going with 2 digits. If you do have something in scientific notation like this, you look at the coefficient to know how to round it. So we're going with 2 digits. I got 1.4 times 10 to the negative 5th. Cool. Units, what would the units be? Negative 5th, yeah. Joules. J. Very good. I think there's one more. Okay, in this third problem with the same scenario, what we're doing is going back to the original force, 2.5 newtons, and instead of relocating it 6.12 meters, he's gonna relocate it at 12 meters. So it should be more work than the first one, right? So work is equal to force, which is 2.5 newtons, times distance, which is 12 meters. Looks like we're going to round it according to 2 digits. Looks like 30. 30 joules. Now here's kind of a little catch we haven't run into yet in lecture. But I said I want to give it 2 digits, okay? And this 30 kind of looks bare, kind of looks like 1 digit. We can actually, in this case, show 2 digits if we hardcore put a decimal in there. Then we have shown it 2 digits. It's a small thing. If you put 30 joules, that would be perfect. But actually, if we put a decimal here after the 0 for 30, then we have shown 2 digits. So it's a small thing. Life's made up of all sorts of small things. Okay, so yeah, we did get to one more assignment. And actually, this is where we're going to stop today. So this will also be due Wednesday. So page 104, short answer number 2. And page 106, exercises 2 and 4. I wonder if, and I don't have those to bring up for you. Sorry. But let me know if you have any problems.
I have a question on my calculator.
Okay.
When I have a negative up here,
So we're done. How many questions?
I can't get that to come from that. This is like 2.5 times.
Oh, did you try this again? Yeah, see, yeah, so it's not this subtraction, it's this plus. And that's right. 2.3, and actually instead of doing the time, instead of doing the time, you do the E. So just push E. Yeah. Awesome.
2.3 E.
Yep. 10. Okay, no. And then when you do that, the next thing is after is -6.
Okay, 2.3, and then E, and then -6.
Yeah.
Times 6.12.
Yay. And yours is, if you want to count it out. There's a way.
I'm just totally confused.
But did that make more sense? So the E actually is saying, okay, I'm in scientific notation. What you gave me was the coefficient. The next thing it wants is the power 10.
And then some of those, I'm like, why is this not coming out to what she